to our first speaker, Andrea Puhm, who will be talking about recent advances in celestial holography. So, Andrea,
hi, can you see my screen?
Slides. Yeah, we see your screen.
Perfect. Okay, can I start?
Yes, you may go ahead.
So thank you very much for the opportunity to speak at this workshop and for the great honor of opening this very interesting looking meeting that discusses holography for everything in our universe. So my task will be to discuss the recent advances in what's called celestial holography. So that will be for lambda equals to 0. And this will, of course, be biased by my own knowledge of the field and my understanding of the field. But I hope to be able to give a broad enough cross-section of some of the very interesting developments that have been going on over the past couple of years and more. But before diving into lambda equals 0 holography, I would like to start by taking a step back and marvel at the ways that gravity acts in our universe. So we have these highly curved regions of space-time. We have moving objects which send out gravitational waves, and we have the full expansion of the universe. And we would like to understand all these different processes in holography where there is no gravity. So this is a highly challenging task. Unfortunately, as a starting point, we are in a lucky position to have very simple models for at least the background on top of which we want to study gravity, and that is these maximally symmetric spacetimes given by de Sitter space for lambda bigger than 0, and the de Sitter space lambda smaller than 0, and Minkowski space for lambda equal to 0. And they all describe, at least to some approximation, these different regions of the universe where gravity acts in different ways. So for lambda positive, it will be very important for understanding cosmology and holography in that context. Then for negative cosmological constant, the region in the universe that will benefit a lot from our understanding in terms of holography are highly rotating or charged black holes. And then finally, on many intermediate scales in between cosmology and the throats of black holes, we have flat space or asymptotically flat space. And this is what I'm going to discuss in the next hour or so. So we want to understand holography when lambda equals to 0. And the first thing to talk about is shown in this beautiful picture that I've stolen from the conference website, which tells us that we should discuss the boundaries of these interesting spacetimes and the de Sitter and flat space. And in this particular context, I should discuss the Penrose diagram of asymptotically flat space, which is this triangle shown here. So what we want to understand is how quantum gravity works in this spacetime, and in particular, whether we can describe the physics and the bulk of the spacetime in terms of a theory living on the boundary that's drawn here in blue. Now, of course, in quantum gravity, the metric fluctuates. And so we will not just have Minkowski space, but fortunately, the causal structure of asymptotically flat space is the same as Minkowski space. So we can start talking about this problem by looking at the structure of Minkowski space near the boundary. And there are three important points here, which are marked on the bottom and the top. And these are time-like past and future infinity. Out here on the right, we have spatial infinity. And then the regions in between, which are these diagonal lines, are null infinity. And we would like to understand whether stuff that happens inside the spacetime can be understood by theory living on the boundary of the spacetime. And in this diagram, of course, at every point here, hiding is a sphere that I've omitted in drawing this radial and time-like plane. Okay, so can we study holography in this context? So first, let me talk a bit about causal motion. So massive particles start out at past time-like infinity and go to future time-like infinity. Spatial geodesics end at spatial infinity. And then we have massless particles which enter the spacetime at past null infinity and exit it at future null infinity. And they do so by entering and exiting at points on a celestial sphere that are antipolarly related. So in this full diamond that I've shown here, I've resolved the two-sphere, where now every point on the left and the right, so a pair of points, denotes this two-dimensional sphere. And it will be very convenient to not talk about the angles theta and phi, but instead use stereographic coordinates z and z bar to talk about the physics on this two-dimensional sphere. So I said massless particles enter and exit at null infinity. These regions are naturally parameterized by a retarded time u and advanced time v. And this happens, of course, where r equals infinity. And one important aspect for understanding gravity in Minkowski space and asymptotically flat spacetime is to understand what happens to the data at the boundary as we approach these special points, I minus, I0, and I plus, and this will introduce into the game boundary conditions as we take the times large or small, and also about how we should relate when we discuss scattering fields near the spatial boundary. Okay, so if we want to understand gravity in asymptotically flat space and in particular holography, the first thing to look at is the S matrix, because that's the basic observable of quantum gravity in asymptotically flat space. So the question is whether we have a holographic picture at the boundary as we look out to null and time like infinity. And this, starting from the center of the space-time, will reach the celestial sphere at the boundary. So the first question is, does the S matrix have any holographic flavor? And indeed, we know because the S matrix is determined by a set of asymptotic data, namely the on-shell momenta, that it already has some kind of holographic flavor. But this holographic flavor becomes particularly crisp when we realize that there is a basis that's more suited for understanding questions about holography. And in this new basis, the S matrix, we will see, will take the form of a correlation function of operators that are inserted on the boundary of asymptotically flat space, namely at points on the celestial sphere. And these operators will also be labeled with quantum numbers delta and j, which will be the quantum numbers under the conformal group. And so the hope here is that at the boundary of asymptotically flat space, we will have a conformal field theory that encodes information about what's going on in the bulk. But even without talking about holography, recasting the S matrix in this new basis provides us a new framework for discussing quantum field theory scattering. And there are some very interesting aspects that become manifest when recasting the S matrix in this new basis. So these properties are that the symmetries, in particular the ones that we're interested in for holography, such as conformal symmetry, become manifest. Certain limits and universal behaviors of scattering amplitude become reorganized in an interesting way. So this includes soft and collinear behavior of amplitudes. And another interesting aspect is that this new basis here is highly sensitive to the ultraviolet. So it probes all energy scales. And so there's interesting room for supersymmetry and for string theory. Okay, so most of us would be interested in really understanding a holography for asymptotically flat space. And the first thing to point out here is that the Lorentz transformations of Minkowski space act as the global conformal transformations on the celestial sphere. And so in this sense, we will have a map between a 4D Minkowski space and the two-dimensional celestial sphere. And so this CFT will live on this two-dimensional celestial sphere. And so the questions that we have to ask here when looking at this map is, what are the operators? What is a good basis of states? What is this CFT even? Is it local? Is it unitary? Is it some more kind of exotic conformal field theory? Is there an organizing principle? Can we bootstrap some sectors of this theory? And then ultimately, of course, can we use it to say something new about quantum gravity in the bulk? So the question that I will be having at the back of my mind throughout this talk is whether we can describe quantum gravity via a theory that lives at the boundary of asymptotically flat space, which will be given by this two-dimensional celestial sphere. And here in this cartoon, of course, I have omitted some other interesting physics that could be going on, such as the creation and evaporation of black holes, which of course is also an interesting question in the context of holography and quantum gravity. But the first thing that we should understand in this game here is what is going on with gravitational scattering when lambda equals 0. So I should maybe also pause for a moment and say that I'm very happy to take questions during the talk. You don't have to wait until the end, so please jump in at any point when something is not clear, or if you want me to expand on something. Okay, so now let's discuss gravitational scattering. So I already mentioned that in quantum gravity, the metric fluctuates, and so we will not have just flat space, but there will be corrections. And the first thing to do is to pick a good coordinate system that lets us clearly see what is the data at the boundary of asymptotically flat space. And a good coordinate system will have gravitational waves propagating outwards. So R goes to infinity at fixed retarded time u when we want to reach future null infinity, and similarly if we want to go to past null infinity. And such a coordinate system has been discussed by Bondi, Sachs, and many other people. And they impose certain constraints on the metric coefficients, as shown here. Once we've fixed a suitable coordinate system, we then have to specify boundary conditions. And this is in general a rather tricky business, because you want the boundary conditions to be weak enough so that you capture interesting physics. For example, you want gravitational waves to reach the boundary. But they should be strong enough so that you don't get any pathologies like energies blowing up. So this has had a lot of history, goes back to the 60s in a sense, where Bondi, van der Broek, Metzen, and Sachs had their seminal work where they discuss boundary conditions of asymptotic flat space, because they wanted to understand the symmetries of general relativity in asymptotic flat space. And so the boundary conditions that they proposed are given here. So the first line in this line element is just the exact Minkowski metric written in this retarded Bondi coordinates that are given by u, r, and then the stereographic coordinates z and z bar. And this gamma zz bar here is just the metric on the unit 2 sphere. Now, in addition to Minkowski space, you have these 1/r corrections, which are given in the second line. And as you can see, there are certain functions that appear in this expansion, and these functions define the radiative data at the boundary. So here I've written this for the retarded coordinates, so this will be defining the radiative data at future null infinity. So this is given by these three functions shown here in blue. The first MB is the Bondi mass aspect, the second is NZ is the angular momentum aspect, and then the capital ZZZ is so-called gravitational data. The first two describe the angular densities of energy momentum and angular momentum, while the gravitational data captures gravitational waves. Its time derivative, so it's retarded time derivative or advanced time derivative, gives what's called Bondi-News tensor. And the Bondi-News tensor essentially tells us about the change of the data at the conformal boundary. So starting from this asymptotically flat metric, we then want to ask what are the symmetries of the space-time, because we need that in order to start understanding a potential holographic theory living at that boundary, which should have the same symmetries. So this brings me to the point of what is the asymptotic symmetry group. And essentially this is defined as all the allowed diffeomorphisms modded out by the trivial ones. So what I mean by this is that we want to find all the diffeomorphism vector fields that preserve the boundary conditions that I have shown on the previous slide, so that preserve the form of the metric. The coefficients of this 1/r terms can change, but the power in 1/r has to stay the same. So we want to look at all the diffeomorphisms that keep this radial fall-off structure the same. And they also have to satisfy exactly these gauge conditions. And since we are not no longer have isometries, we have a more relaxed condition given by the Lie derivative of this vector field acting on the metric. And so we want to have this be 0 asymptotically as we take r to infinity. And then all the diffeomorphisms that preserve these fall-off conditions and Bondi gauge can be written in this form in retarded time coordinates. And so these are all the allowed diffeomorphisms. And when we mod out the trivial diffeomorphisms, what we mean is that we can have diffeomorphisms that fall off at the boundary. So they're only present somewhere in the space-time, but they fall off at the boundary. And so these are redundancies of the theory, and so by these we will mod out. And then all the diffeomorphisms that will change the state at the boundary, those will be the residual ones that define the asymptotic symmetry group. So for translations and Lorentz transformations, this function f and vector field y that's showing up in this diffeomorphism vector field take a certain form. For example, if we take y equals 0 and f equals 1 in this vector field and look at the boundary, then this diffeomorphism just reduces to global time translations. For Lorentz transformations, in order to preserve the fall-offs of the metric, we have to satisfy the conformal killing equation on the sphere, which is given by this equation written here, dz bar yz equals 0. And so these are global conformal killing vector fields. So this makes up the Poincaré group, which has 10 generators. But to the great surprise of Bonny, van der Burg, Metzner, and Sachs, and probably everybody else around that time, this is not all they found. Instead, they got infinitely many generators for the asymptotic symmetry group. And this is now known as BMS group. And so what happens here is that rather than having f be a constant or a specific function of z and z bar, we allow f to be an arbitrary function. And an arbitrary function of the sphere then gives us infinitely many more choices. And so the BMS group is then given by what's called now super translations, so the infinite enhancement of translations, and the Lorentz group. Now one can then ask, do the Lorentz transformations, so the rotations and boost, also get infinitely enhanced? And from this, one has to relax a little bit the boundary conditions. And what one then finds is that if one chooses this vector field y to be a holomorphic but otherwise arbitrary vector field, or to be even a non-meromorphic vector field, then we also get an infinite enhancement of the Lorentz group to super rotations. And the difference between these two choices of being meromorphic or not will be a difference in whether we have a Virasoro or a diff-S2 symmetry. Okay, so this is an infinite enhancement of the usual symmetry group in special relativity. And this is only actually the tip of the iceberg if we want to talk about the infrared physics of gravity in asymptotically flat space. Or in other words, it's only the corner of what's now known as the infrared triangle. So there are
Andrea.
Yes?
Hey, quick question. Can you say what happens in dimensions bigger than 4?
Not now, not in a short time. And so the thing is, if you pick boundary conditions, so here, for example, in order to not have logarithms, you have to pick a certain gauge. Now in higher dimensions, the story, you will have to redo the story for whatever dimensions you are in. Now, of course, you don't, okay, so this Virasoro symmetry group you won't get, but you might get it so there's a high dimensional sphere in high dimensions. But I don't know how much of the story that I'm gonna tell will go through with higher dimensions. Some form of it surely will, because here there are relations between asymptotic symmetries and some other areas where we clearly know what's going on in high dimensions too exists. But okay, so let me make the point here. So memory effects will be related to certain shifts of components in the expansion in non-infinity. And depending on which dimension you are in, those will be at different orders. And also different gauges, if you pick different gauges, this will be at different orders too. And so there has been some debate about whether memory effects exist in high dimensions or not. And so this story for asymptotic symmetries and memory effect is very much tied to boundary conditions and in which dimensions you are. So I don't have any as conclusive statement to make in high dimensions as there is in 4 dimensions.
But could you say at least if one expects an infinite dimensional symmetry or not? Like if we just had, conformal symmetry in 3 dimensions, it would not be infinite dimensional.
Yeah.
So does that intuition go through? Or
I think
is it not
here,
clear?
so I think this is special to 4D because it relates to 2D where we have this infinite enhancement of
exactly
global conformal group. I don't know what the possibilities are in high dimensions other than that. So the infinite enhancement is special to 2D, it seems, but also there are many other things that are special to 4D, like infrared divergence is also, this is also special to 4D. And also in any case, we live in 4D, so whatever is special to 4D, this is important to pursue. But of course, we expect the general statement that can be made here, which is that there should be some form of holography in a codimension that relates codimension to, so a codimension tool holography where the bulk is d-dimensional and the boundary theory is d-2-dimensional. But I don't know to what extent this resembles, will resemble this 4D 2D picture on which I'm focusing on here.
Thanks.
Can I ask something related to the comment that you just made about the absence of logs? Is
Yes.
there a specific reason why you don't want logs? Could you not allow for some Weil anomaly in the CFT that would capture these logs? Is there?
I think maybe the first statement is that logs are tricky, but then indeed you could allow logs, and there have been some interesting works by Sen and collaborators that find other memory effects that come from logs. For the purpose of this review, I will just focus on the boundary conditions that were proposed here in the 60s. But of course, you can always relax them. And indeed, so you can relax them, but then you have to see whether anything bad happens. One thing that if you want this infinite enhancement and furthermore the full DFS2 symmetry group, you will actually have to relax these boundary conditions. Maybe let me make a comment here since we're talking about memory effects and so on. So here, if you want these meromorphic vector fields that are local conformal Killing vectors and not just global ones, then you need to relax these boundary conditions, at least at an isolated point. There will be a component of the metric that does not satisfy these conditions everywhere, but at a point it will be violated, this conformal Killing equation. If you want to allow for arbitrary vector fields, then this will be violated everywhere. So for the meromorphic ones, this will be violated at a point. So the z bar yz will be a delta function. So even for the DFS2, boundary conditions get violated, and the interpretation physically for what happens in the case of where this vector field is meromorphic is that you have cosmic strings. So yeah, in principle, you can allow for more relaxed boundary conditions, but then you have to see that nothing bad happens. And logs often tend to make bad things happen. Yeah. Okay, so this is just one corner of interesting infrared physics that's going on. I mentioned already memory effects, which will not be to highlight in this review, but the other corner of this triangle will, and that's soft theorems. So these are universal aspects of quantum field theory scattering amplitudes, which are related to asymptotic symmetries, and I will talk about this relation in a bit more detail. The memory effects can be viewed as the Fourier transform of these momentum space soft theorems, and then can be related to asymptotic symmetries as being the physical effect of having a vacuum transition that's generated by these asymptotic symmetries. Because asymptotic symmetries, maybe I should emphasize this, is since the parameters for the symmetry don't die off near the boundary, and the action of these asymptotic symmetries will change the state. And so this change of state can be encapsulated by memory effects. Okay, so I will mostly talk about gravity and the two important triangles that one has to discuss, which is the first is the infinite enhancement of translations so that we get super translations. And that's related to the so-called leading soft graviton theorem of Weinberg from the 60s. And on the other side of this triangle is related to the so-called displacement memory effect. And interestingly enough, these are all things that happened around the same time, but the connection was only made rather recently. Now, if we also generalize or enhance the Lorentz group to superrotations, then we have the relation to the subleading soft graviton theorem, which was also found only recently, and the so-called spin memory effect. So now let me talk a little bit about this soft theorem corner of the triangle, because that will be quite important for going towards celestial holography. So this is the statement that gauge theory amplitudes have a universal behavior when the energy of a gauge boson that's participating in this process is taken soft or otherwise taken to zero. So in gravity, the statement is the following: if I have an endpoint amplitude with the insertions of a soft graviton, and I take this energy to zero, then the amplitude will factorize into one without the soft graviton, and then there will be a universal factor. And so the first term here is the famous Weinberg soft pole, where we have a pole in 1 over the energy, and then a universal factor that's given by an expression in terms of the momenta of the hard particles, the soft momentum of the soft graviton, and its polarization tensor. And then furthermore, there is a second universal factor, which goes like omega to the 0. And this also has a universal factor where now we have this depend on the hard momenta, but also the hard angular momenta. And I've chosen here a gauge where I can write the polarization tensor as a product of polarization vectors. Now, gauge invariance of the soft factor, which means we shift the polarization tensor by something that's proportional to epsilon times q, where here I should say I'm in a gauge where epsilon dotted into q is 0 and q square is 0, so that this polarization tensor is only defined up to this shift. And what happens when we do this shift, we find that the gauge invariance of the soft vectors is ensured by global energy momentum and angular momentum conservation. So there's an interesting interplay of conservation laws and soft theorems. But actually there's much more here, namely the soft graviton theorem implies not only these global conservation laws, but it also implies BMS symmetry. So that is the statement that the charges for super translations, but then also for super rotations on the past boundary and the future boundary are actually equal. And there's an infinity of these conservation laws for every function f and vector field y. And how does this arise? So this arises as follows. So what we have to show is that the commutator of these charges with the S matrix vanish when sandwiched between in and out states in an S matrix element. The charge for BMS supertranslation and superrotation symmetry is given by this expression that involves the bonding mass aspect and the angular momentum aspect. And what's convenient here in order to show that BMS is a symmetry of the S matrix is to split the charges into what's called a hard part and a soft part. So the hard part will be quadratic in the asymptotic data, while the soft part will be linear. And what we want to do, so we plug in this splitting into this commutator here. And so what we want to do is we want to show that the left-hand side here involving the soft charge corresponds to the insertion of a soft graviton. And the right-hand side, we can compute that, and we find that it's proportional to the soft factors that I've shown you before, times the original S matrix element. And now if one can show that this is indeed, the left-hand side is indeed a soft graviton insertion, then we can use the soft theorem to show that this equality holds. And then that means that that BMS is really a symmetry of the S matrix. And to do this, we look at what the expression for the soft charges is. Here we have this supertranslation F and the superrotation Y, but also we have the asymptotic data in these U integrals here. And what one can show is that when one integrates the gravitational data C, and then uses the fact that such integrals in U become limits when the energy is taken to 0, then we can recover that the left-hand side is indeed a soft graviton insertion. And then by the soft theorem, we know that the left-hand side becomes the soft factors times the original S matrix element. And in that way, one can show that soft theorems imply, because now the soft factor is written out here, and I'm only left with the matrix element that doesn't contain any insertions anymore. In that way, we get that soft theorems imply word identities for asymptotic symmetries. Okay, so one more point about this here. So the first lines here, respectively, are the soft graviton theorems. I'm starting here with a subleading one. So this can be massaged into the expression written at the top. while for the leading soft graviton, it can be massaged into the expression written up here. Now, the thing is that the leading and the subleading soft graviton theorem, they imply a symmetry of the asymmetrics, but they also give us these soft and hard charges. And it turns out that the insertion of soft gravitons can be interpreted as the insertion of respectively a stress tensor and a current. So if we look at this, the first line up here, this looks very much like the water density for a stress tensor, if we compare the first two lines. And in order to make this precise, we would have to have a basis where this operator omega, the omega acting on the S matrix, becomes a number. And so if we want to interpret the subleading soft graviton theorem as the insertion of a stress tensor and a correlation function, we have to change the scattering basis. Similarly, for the leading soft graviton theorem, and here I've written essentially a sphere derivative acting on the soft graviton insertion. If we compare this to the water density of a current in a CFT, then we also see that we have to find a new basis. And furthermore, the new basis will obscure, in a sense, translation symmetry, because somehow this factor of omega has to go away. And the way it will go away is that it will do something to an operator in this correlation function. So this slide is to give sort of a hint that there might be an underlying conformal field theory that is related to the S matrix. And in order to find this conformal field theory, what this is telling us is that we need to find a new basis for the S matrix. So from this slide, the takeaway message is that for the quantum field theory soft theorems, they look like water densities in a two-dimensional conformal field theory. And now let's see what it takes to get to this conformal field theory. Okay, so in principle, I will have to discuss two things. I will have to discuss how we map from the energy momentum basis to a new basis for massive particles, but also for massless particles. So in the S matrix, we specify the on-channel momentum for the in and out states, and massive particles will be parameterized by a point on this hyperboloid, while massless particles will be parameterized by this cone of null momentum. And it turns out that the map that takes us to a basis where these water densities become manifest is given by the following integral transforms. So on the left, we have an integral involving this hyperbolic slicing coordinates and the bulk to boundary propagator, while for massless particles, this integral transform is simply a Mellin transform in the energy. And these two integral transforms that will introduce a new parameter, delta, which will turn out to be the conformal dimension of the operators that I've shown you on the previous slide. So in CFT, we specify these conformal dimensions, but we also specify the point on which we insert these operators. So for now on, I will mostly focus on the case of massless scattering. So this will just be the map from for the bulk S matrix to a boundary correlator will just be given by this Mellin transform.
Andrea, can I ask a question before you go on?
Yes, please.
So this this word identity structure, does it only arise in the case where you pick boundary conditions such that you have this Virasoro algebra acting on the? Yeah. So otherwise, you will.
So if you don't have you only have the global conformal group if you don't relax these boundary conditions at a point.
Well, yeah, I was more wondering what happens in the case where you allow for all of diff S2. Do you know what?
Yes. So in that case, we will see this later on. In that case, you will get the shadow stress tensor instead of the stress tensor. So the shadow transform is another integral transform now in 2D, which is a smearing over the sphere. And I will show in a bit that naturally, when we go to this new scattering basis, you can naturally get the stress tensor. Maybe we'll hold this question until I actually show you the slides where I do this. But yeah, indeed. So here you get a stress tensor. It has this holomorphic water density, but then you can also have the shadow stress tensor, and that will not have a holomorphic water density. Yeah, I can come back to that later on, or maybe you ask your question when I get to that, if there's a more specific point. Okay. Okay. So yeah. So now let me discuss wave functions. So I will focus on the massless case from now on. So if we do a Mellin transform of on-shell plane waves, we get something that's gauge equivalent to what we call conformal primary wave functions. So these wave functions depend on a bulk point x and the boundary point on the sphere w and w bar. And we require them to transform as 4D spin S fields under Lorentz transformations and as two-dimensional conformal primaries with a conformal dimension delta and two-dimensional spin j. And let me point out here, the spin S here does not in general have to be equal to the magnitude of the 2D spin, but for radiative wave functions it is, and that's what I've shown here. So these wave functions have to transform under Lorentz transformations and conformal global conformal transformations, which are just these Möbius transformations on the celestial sphere. And that's the statement that I've written here, where this D here is just the four-dimensional spin S representation of the Lorentz algebra, depending on what indices this conformal wave function has. So this can be a scalar or vector or whatever spin you want. Okay, so when the 2D spin is equal up to a sign to the four-dimensional spin, then we call these wave functions radiative. And furthermore, we ask them to solve the linearized equations of motion for massless spin S fields. So for example, the massless Klein-Gordon equation for scalar, or Maxwell's equation for vectors, or the linearized Einstein equations for spin 2 wave functions. But then we can also be a bit more general and allow for sources and distributions. And in that case, we will want to relax the condition that 2D and 4D spin are equal. And that will be turn out to be a good idea. Okay, just to be a bit more precise. So for the scalar, we have just the scalar plane wave. And the Mellin transform of that will give us the spin 0 conformal primary wave function, which is given by this expression 1 over this null vector q, which points towards the celestial sphere and whose parameterization I've given up here, and then dotted into the spacetime vector and to the power delta. So the power of this 1 over q dot x expression will be the conformal dimension. And then for spin S particles, I have to dress them with the appropriate polarization vectors or tensors or spinors if you want to discuss massless fermions. So let me just maybe focus on the spin 1 and the spin 2 case, where the polarization vector is a space-time dependent one, and it can be constructed in part from this null vector q, which gives us a natural polarization vector, which is space-time independent. But then for these wave functions to actually transform as conformal primaries, I have to shift and make them space-time dependent. And so this is now the set of spin S conformal primary wave functions, which will form a basis of wave functions in this celestial CFT. So once I have this wave function, I can construct two-dimensional operators. These two-dimensional operators are given by an inner product of a bulk operator, which we can expand in modes. So for example, we take the bulk operator of a spin 2 field, expand them in modes, plug them in here, compute the inner product with a conformal primary wave function, one of the ones that I've shown you before, and compute that integral. So that will be an integral over a Cauchy slice in the bulk. And so the result of that will be an object that depends only on the boundary. And it will be a two-dimensional celestial operator, which is labeled by conformal dimension delta and spin j. And here one thing to point out is that this operator will carry a plus-minus label, and that plus-minus label essentially tells us whether we're talking about in-states and out-states. So here, the celestial sphere, the boundary will be a single celestial sphere, and whether we have in-states or out-states will be distinguished by this label. Okay. So now we have wave functions and operators. Now we can talk about amplitudes. So we want to recast the scattering amplitude in terms of a correlation function on the sphere. And now I've told you what kind of operators will show up in this correlation function and how you can get them from 4D bulk wave functions. And let me emphasize again, what's behind the scenes here is that Lorentz symmetry SO1,3 acts on a celestial sphere as the global conformal symmetry SL2C. And so this is why we can write the amplitudes in this nice way in terms of correlation functions of operators. Now, because the amplitudes are constructed in that way, namely with these Mellin transforms of the momentum space amplitudes, and because we now have changed this transform changes the basis from energy momentum eigenstates to a conformal basis, by construction, the amplitudes that we obtain, which we call celestial amplitudes, denoted by this tilde here, will naturally deform as conformal correlation functions when these boundary points are taken to transform on the Möbius transformation. Okay, so celestial amplitudes are interesting because they make conformal symmetry manifest, and it's in that sense that they provide a novel opportunity to study properties of scattering amplitudes. Okay, so the transform, the Mellin transform, can easily be inverted if the conformal dimension is on the principal continuous series of the Lorentz group, which means the real part of delta is 1, and the imaginary part is any real number. And this principal continuous series delta contains essentially finite energy radiation. So if you take the on-shell plane waves and you Mellin transform them, the fact that the plane wave basis was delta function normalizable translates into this new basis being delta function normalizable, but the delta has to be constrained to lie in the principal series. Now, if that's so, then we can invert the Mellin transform in that way. But it will also be interesting to move away from this principal series and consider general complex dimensions. And that will be particularly important when making connection to asymptotic symmetries. Another thing to point out is that in this new basis, translation symmetry is no longer manifest. The translation operator in this new basis can be represented as this exponential derivative operator with respect to delta, which has the effect that when it acts on operators or states, it will change the conformal dimension from delta to delta plus 1. So it shifts the conformal dimension and takes us away from the principal series. So it will be important to really understand the spectrum of general delta and not just the ones that we obtain naturally from the plane waves. Okay, so then let me make connection to soft terms, which I started with. So there the statement was that the amplitude factorizes into these universal pieces times the amplitude without the soft insertion. And it turns out that the orders of this expansion, so 1 over omega, omega to the 0, actually translate into poles of the celestial amplitude at special values of delta. So you can see this here. So this number here corresponds to this number in the Mellin transform. And when we look at the low energy limit, so the soft limit of this integral transform, we will find that there are poles at certain values of delta. And this will be a delta equals 1 for the leading soft graviton and the delta equals 0 for the subleading soft graviton. So just here shown as an example, the leading soft graviton, which has this pole in the energy. What will be important here is this current that I had introduced before when talking about water densities. So this is a so-called supertranslation current. It's OPE with an operator of energy omega, has this explicit power of omega here. In the new conformal basis, and this extra power of energy will translate to a shift in the conformal dimension delta. And this is related to the fact that translation shifts the conformal dimension. Okay, so orders of omega in the soft expansion correspond to poles in celestial amplitude in a so-called conformally soft expansion. And one first thing to note is that this is a rather unusual looking OPE, and is one of the indications that this dual celestial CFT is not quite a vanilla CFT as we're used to in many other contexts, but of a more exotic kind. Okay, so now let me make contact to asymptotic symmetries. So these are related by the triangle to the values of delta at which celestial amplitudes factorize and have these poles. And these values are not on a principal series, but they are in the integers, or if you want to also include fermions, in the half integer values of delta. So what we want to look for here is for two-dimensional operators that generate these four-dimensional asymptotic symmetries. And it turns out that this happens when we compute these two-dimensional celestial operators from these integrals over Cauchy slices where the conformal primary wave functions reduce to pure gauge. So when that is the case, then this two-dimensional operator is a symmetry generator. So I've listed here all the possible cases where these wave functions become pure gauge and give rise to an asymptotic symmetry generator. So for example, I mentioned before, super translations give rise to a super translation current, and super rotations give rise to a stress tensor. And then a question came up about what happens when we have diffs 2. Yeah, there we have the shadow stress tensor, which is also a symmetry generator in this new basis. And so for any energetically soft pole, we now have a value of delta that gives us a conformally soft pole in the corresponding celestial amplitude. And so we can understand 4-dimensional symmetries, asymptotic symmetries from a basis of 2-dimensional currents. Okay, so maybe let me just say quickly. So the wave functions that become pure gauge are listed in this upper table. One thing to point out is that there is what's known in the literature as a double copy or Churchill double copy, which relates spin 1 and spin 2 fields. And here we can say that BMS symmetry can actually be understood as a large gauge symmetry. There's a corresponding statement for the spin 2 fields that gives us super rotations. But now the double copy relates it with a gauge field that's not pure gauge. And in fact, the other conformal primary wave functions or values of the conformal dimension for which the celestial amplitudes factorize, but these wave functions, none of them is pure gauge. And so there is an interesting situation where we have conformal soft theorems that either come from pure gauge modes or that come from non-pure gauge modes. But actually it turns out that can be unified in one framework, and I will talk about that in a moment. Another thing that came up is because we had this discussion about Virasoro versus diffs 2 and the appearance of the shadow transform. So that takes an operator or a wave function that has a certain conformal dimension and spin and shifts it and flips the spin. This is a 2-dimensional integral transform, and there exist corresponding symmetry generators for these shadow modes. Again, there exist pure gauge modes, which then give rise to the stress tensor or the supersymmetry current. And then there exist also non-pure gauge modes, which also give rise to soft factorization theorems. And they can all be the values at which the celestial amplitudes factorize can be uniformly captured by looking at the global conformal multiplet structure. So in a CFT, if we have a primary state that's annihilated by L1 and L bar 1, then we can also have primary descendants. So that are descendants that one gets when acting with L minus 1 or L bar minus 1. And these descendants become primaries themselves if they're also annihilated by L1 and L bar 1. And then this gives us the conditions for what the conformal weights H and H bar of the original state have to be. And when both of these conditions are met, then we get a nested structure of primary descendants. So we start with the primary and we find primary descendants at these corners, and then we can further descend with the action of L minus and L bar minus 1 to get another primary descendants. And from the point of view of celestial CFT, this action of L1, L minus 1 and L bar minus 1 just corresponds to acting with derivatives in the celestial sphere coordinate. Okay, so now we have this conformal multiplets. Just as an example, the structure of conformal multiplets for different cases. So say the leading graviton and the subleading graviton has this conformal multiplet structure, where at the left and then the right corner of each of those diamonds lie the pure gauge wave functions, which give us soft theorems. And then we can write down a full conformal multiplet where these pure gauge wave functions descend from some other wave function and then descend at the bottom to some other wave function. And these are these generalized conformal primary wave functions that I talked about in the beginning, where we don't require that the 2D and the 4D spin are equal. Okay, so then these the most subleading soft theorems, which don't come from pure gauge wave functions, then correspond to degenerate diamonds, where we only have one primary to start with and one primary descendant to end on. Okay, so this was just to flash some of the multiplet structure in celestial CFT. Let me now comment on the two different types of primary descendants. So there's one type where we start with a primary from in this shaded region in the delta J plane. And the primary, when you act with these derivatives or with L minus 1 and L bar minus 1, they actually become 0. So there's a value of the conformal dimension, which if you act with enough derivatives, this wave function will become 0. or the operator, the corresponding operator will become 0, and then you get infinitely many so-called null states. And there's been very interesting work recently that looks at how these null states appear in celestial amplitudes, and there's actually an interesting W1 plus infinity algebra that celestial amplitudes obey. In the other case where we don't land on zero wave functions, but we can land on, let's say, delta functions, is in this case where we have the conformal soft theorems appearing. So for example, you have two primaries that descend to the same primary. This is the case where we'll have the leading and the subleading soft graviton theorem. There's also a sub-subleading soft graviton theorem, which I haven't shown you, but this corresponds also to a value of conformal dimension, which appears in these conformal multiplets, and it's of this degenerate type. Okay, so this was just to sort of give a flavor of the structure of multiplets in celestial CFT. And now let me maybe point out two more things. So if you look at the operator that generates super translations and super rotations, I already mentioned that they have to do with the left and the right corners of this conformal multiplet structure. The soft charge for super translations is obtained from the operator sitting on the left or the right of this leading soft graviton diamond. The super translation current that I mentioned before is actually not a primary here. It sits on this corner here, which is a descendant but not a primary. And that explains why in the Kac-Moody word identity we had to have this extra derivative acting on the soft insertion. So then in the subleading soft graviton theorem, we have soft charges which correspond to the left and right corners of this subleading diamond. And this corresponds to either the stress tensor in the 2D CFT or the shadow stress tensor. And this one on the right has to do with Virasoro symmetry, while the one on the left has to do with DFS2 symmetry. And the two are related by this two-dimensional shadow transform. Now, each of those, the stress tensor and the Kac-Moody current, sit one derivative above the bottom corner of these diamonds, and these are holomorphic currents in the CFT. And we will hear more talks by Laura and Romain that talk about BMS flux algebras, which are related to the bottom corner of these diamonds. So the bottom corner are certain soft operators, which generate the asymptotic symmetries. And they generate the asymptotic symmetries by, how to say this? So the soft charges correspond to the insertion of these soft operators smeared by these symmetry parameters F and this vector field Y. And so now we understand from the structure of the celestial CFT how asymptotic symmetries arise. They arise from the action of these soft operators, which rise in this conformal multiplets. Okay, so now another thing that arises in this context is dressing. So if we have these soft theorems and we look at amplitudes without soft radiation, then infrared divergences exponentiate and the amplitudes vanish. And this can be interpreted as a non-conservation of the charges that generates the asymptotic symmetry transformations. Now, a way to get infrared finite amplitudes is to dress the hard operators with certain dressing factors that cancel these infrared divergences. So here I've written the dressing for the leading soft graviton. It's given by this expression. We call it the conformal dressing when we take this in principle arbitrary but constrained function to take a certain value. And when we do that, then the dressing takes a very simple form. It takes the form of a vertex operator where we have an appearance of the energy and we have an appearance of this function C here, which turns out to be a Goldstone boson that shows up in conformal multiplets in celestial CFT. Now we can rewrite this operator here in the celestial basis by noting that this extra power of omega can be replaced by the action of the supertranslation current, which gives this extra power of omega, or in the conformal basis gives this shift in the conformal dimension. And then what we can do is we can look at the full Mellin transformed amplitudes, which factorizes into a soft and a hard part. And the soft part is given by this very interesting correlation function of these vertex operators that involve this Goldstone boson Z. And now if we dress the bare hard operators by this Goldstone boson C, infrared divergences get canceled, and the remaining hard amplitude is a dressed amplitude and is an infrared finite observable. So celestial amplitudes have this very natural conformal dressing where we can nicely write infrared safe observables. And the way to do this is by having this very interesting correlator of these vertex operators, which brings me to the next topic, which is that can we capture at least some subsector of this celestial CFT in a simple way, and a subsector that has a good chance of being understood in a holographic context is the conformally soft sector. And this conformally soft sector involves precisely these Goldstone bosons that appear in the dressings. So this sector captures the spontaneous symmetry breaking dynamics of four-dimensional asymptotic symmetries. And we can look for simple effective two-dimensional models. One such model is the free bosons, which captures the spontaneous symmetry breaking of a large U1 gauge symmetry. There's also a corresponding model for a non-abelian gauge theory. And here I've shown the effective 2D action for the case of gravity, namely for the supertranslation Goldstone mode that I've shown on the previous slide. So there exists a simple action, 2D action, which describes the symmetry breaking dynamics. And with this action, one can recover also the correlation function of these Goldstone bosons, which gives levels for, or in general, essential extensions for the celestial conformal field theory. And these levels are captured by Caspar anomalous dimensions. So the two-dimensional conformally soft sector has some very interesting dynamics, and at least the free part has very simple toy models that capture it. Okay, let me maybe skip the next slide and come to another topic. Maybe I should ask at this point, is there any question on, let's say, conformally soft physics, asymptotic symmetries? If not, I change gears a little bit and talk about collinear limits and connection between infrared and ultraviolet. Okay, so now let me talk about collinear limits of amplitudes. So if I parameterize the momenta in terms of the expressions that I've shown you on a couple of slides ago in terms of energies and points z bar on the celestial sphere, then it's easy to see that having collinear limits between particles in an amplitude corresponds on the celestial side to taking the location of two operators close. So taking Zi to Zj. And now this means that the collinear limit of amplitudes captures celestial OPEs, or the other way around, celestial OPEs capture collinear limits of amplitudes. We can show this by either doing a brute force computation of the Mellin transform of collinear amplitudes. So in the amplitudes side of things, we know that we can get the collinear limit. We can write this in terms of a function called a split function, and an amplitude where the momenta of the two particles which we take collinear are replaced by an overall momentum, same as for the energy. And then the information about the individual momenta is hiding in the split function. Now we can say we want to study the OPE of two operators at location Zi and Zj, and we take these to be close. Then to obtain this OPE, we Mellin transform in the ith and jth energy. We Mellin transform the split function acting on this state with total momentum P. If we do this for the case of graviton, the split function, where now the helicities are all 2, is given by this simple expression in the energies and the coordinate Z. And then we find that the OPE between two such operators, two such graviton operators, is given by this simple looking expression, where the coefficient in the OPE is given by the Euler beta function. So this is this ratio of gamma functions. So this is a very interesting result. The OPE of two celestial graviton operators involves the Euler beta function. Now, very interestingly, rather than doing this sort of brute force computation of Mellin transforming the collinear limit of amplitudes, we can also get this OPE by symmetry considerations. So we expect the OPE to take this form. And let me just point out that if one of these operators is the super translation current, then there's an extra derivative hitting. And so this will just become a 1 over Zij. And so look like the OPE of a current. So now the OPE of two general gravitons is generally given by this expression, and we want to determine this coefficient C from symmetries. Now there's a couple of recursion relations and constraints for this coefficient C. So for example, translation invariance tells us that the Z is related to itself with shifted conformal dimensions in this form. We know from the leadings of graviton theorem that residue of a pole when the conformal dimension is taken to 1, which is the special conformally soft value, then the coefficient is given by this expression on the right. And we also know from the sub-sub leadings of graviton theorem, which I haven't really talked much about, that there's an extra constraint, and this extra constraint will give an extra recursion relation. And then taking all of these together determines this coefficient C, and we land again on the expression from the previous slide, namely that it's given by the Euler beta function, where the arguments are the conformal dimension of the operators. Okay, so we understand celestial OPEs from collinear limits as well as from asymptotic symmetry considerations. Now, one thing that I haven't told you before is that actually low point celestial amplitudes are singular. So if we perform a Mellin transform of an n-point amplitude, so these are n such integrals, we can rewrite this in different coordinates that make manifest what kind of structure or constraints the amplitude will obey. So if I take a new variable to be the sum of all the energies, so that's the overall coordinate omega, and then I define sigma j's, which are the rescaled individual energies. Then doing this integral transform tells me that there will be a delta function that constrains the sum of these new variables. Similarly, if I plug in the amplitude, which is given by a stripped amplitude and the 4-dimensional energy momentum conserving delta function, this will also give me at the end delta functions in the new amplitude after I've performed the Mellin integrals. So in general, if the number of particles involved in the scattering process is smaller or equal than 5, then some of these delta functions, some of these 5 delta functions will remain in my final celestial amplitude. So that the final celestial amplitude has kinematic singularities, which arise either in the positions Zij's or are constraints on the conformal dimensions. And there's recent interesting work that tries to tame these delta function singularities and make them more like power law, such that the celestial amplitude looks much more like a vanilla celestial CFT correlator. And these recent works use in particular shadow transform, but also twistors up here. Okay, maybe the last 2 things that I want to mention is that one is about conformal block decomposition and the other one is about the UV sensitivity of celestial amplitudes. So the singularities that I just mentioned have to be reproduced by in celestial CFT. So in particular, if we transform the momentum space amplitude to a Mellin space amplitude, we would have to see these singularities, these kinematic singularities that I just talked about appear. So here, if I look at 2-to-2 scattering and I do this Mellin transform, I will get an expression which contains the Mellin transform of the stripped amplitude and the kinematic factor, which contains, this is a universal kinematic factor, but there's also this appearance of a delta function, which, because I have now 4 points, I have 4 Mellin integrals, I had 5 delta functions, now there's 1 delta function that's left after I've performed the integrals, and this delta function constrains the conformal cross ratios given here. And now if we want to study conformal block decomposition of these 4-point correlators, these delta functions have to be reproduced. And indeed, as shown in this last paper that I've listed down here, summing over all the primaries in the exchange in the conformal block decomposition recovers this delta function. And there are also interesting questions that people think about, which is that I haven't talked about quantization yet in celestial CFD. So there is a natural quantization that arises from the 4D bulk. But there's also, usually we're dealing with radial quantization in, say, ADS-CFD or in usual context, but those are not the same. And so there's interesting recent work that describes how we can recast celestial amplitudes in a different form such that we can use usual radial quantization. Okay, so then another thing I want to mention before closing is the UV sensitivity of celestial amplitudes. So because we integrate over all the energies for massless amplitudes, we no longer have a clear distinction between the low energy and the high energy, and actually celestial amplitudes probe all energy scales. And an interesting aspect is that in general, classical amplitudes like classical gravity amplitudes are divergent after you perform these integrals. But it can be shown that when you go to string theory, these divergences get softened. More generally speaking, we can look at the Mellin transform celestial amplitude and focus in on this piece that I called A tilde that depends only on the sum of all the momenta of the operators and the conformal cross ratio. So I'm just focusing on the second piece here in the celestial amplitude. And this is given by the Mellin transform of the stripped amplitude in the energy momentum basis. And it turns out that if you look at where this expression has poles, in the Mellin transformed celestial amplitude, these poles arise at positive even integers in field theory, because the stripped amplitude takes this form. But then when you go to string theory, where the amplitudes are softened, these poles disappear. And so there's an interesting, first of all, an interesting UV sensitivity to amplitudes in field theory. But then also when we go to quantum gravity, certain singularities get resolved. And so this shows that celestial amplitudes are very nice for looking at analytic structures of amplitudes. Okay, maybe okay, I have maybe 1 minute left or so. So here I just want to mention that I've talked so far about soft limits, conformally soft limits, and the relation to asymptotic symmetries. I've talked about collinear limits of general celestial amplitudes and the UV sensitivity of celestial amplitudes. Another thing that's arising in the amplitudes literature is how amplitudes with different spin are related. And this goes under the slogan of gravity is gauge theory squared. And I think since I'm a bit out of time, let me just mention in words what happens here is that there's a relation between, let's say, gluon amplitudes and graviton amplitudes that involve the replacement of a color factor in the gluon amplitude by another kinematic factor, which depends on the momentum and polarization vectors. And in that way, you can relate Young-Mills amplitudes to gravity amplitudes. And so this is used, for example, now recently in the attempt to use amplitudes method to study gravitational waves. And you can use these Young-Mills amplitudes or spin 1 amplitudes to engineer gravity amplitudes. Now, a lot of what's going on here is using manifest translation symmetry, which gets obscured in the new conformal basis, where instead conformal symmetry is manifest. And so a priori, this relation between gauge theory and gravity amplitudes needn't be there. But if it's a fundamental property of amplitudes, it better should, since we're only changing the basis. And the punchline is that there is also a celestial analog of the double copy, but it requires that instead of replacing functions, we need to talk about operator valued expressions. And so there's an operator valued relation between celestial gauge and gravity amplitudes. And there's also similar results for ambitwistor strings in ADS. And one can also get interesting insights about this relation from the string worldsheet, the ambitwistor string worldsheet. And the final thing that I want to say is that so far I've talked about perturbative amplitudes, wave functions, and operators. But actually we can also capture finite gravitational backgrounds in the conformal that transform with definite conformal weights. And And that's because these conformal primary wave functions satisfy what's called the Kerr-Schild double copy. So that means that if I perturb Minkowski space by these conformal primary wave functions, this vector M turns out to be null and geodesic with respect to the flat and the full metric. That's a so-called Kerr-Schild vector. And it means that these wave functions are actually not only linearized solution, but also exact solution to Einstein's equations. And an example of such an exact solution that has definite conformal weights is the Eichelborg-Sechsler shock wave or ultra-boosted Schwarzschild, as well as ultra-boosted Kerr. So these shock waves can be written in a form where they look like perturbations of Minkowski space, but they're exact solutions, and these are described by conformal primaries where the 2D spin is not equal to the 4D spin, so generalized conformal primaries. Okay, so there's much more going on, and I'm sorry that I could not cover all the interesting recent developments that have been going on over the last couple of years. I hope I've given some cross-section, and now let me just summarize that. So we want to understand celestial holography, the attempt to study or get a holographic principle in asymptotic flat space. I've shown you that in this context, the asymptotic symmetries are made manifest, and it gives a new framework for studying scattering amplitudes. The soft and collinear behavior has been reorganized in a way so that we get word identities and connect this to asymptotic symmetries. And there's an anti-Wilsonian paradigm going on here, and so there's interesting room for theories of quantum gravity. And then, of course, the big question is, can we use this celestial CFT and what we have learned to say something new about gravity in the bulk? So this is just really the story beginning, and there's much more to be learned. So let me thank you and stop here.
So thank you, Andrea, very much. So any questions? Yeah, please raise hands. So Dionysius is the first to go.
Hi, Andrea. Thank you for the nice talk. I had a quick question. So regarding the holography picture, it's not that just because we have a celestial sphere that we've removed sort of the radial direction of flat space, right? We've just encoded it in a continuous infinity of operators living on the celestial CFT.
So here I'm not sure what your question or comment.
I just wanted to confirm whether I'm understanding the bulk dimension of flat space in the celestial picture is this continuous collection of operators on the celestial CFT, whatever that 2D object is.
Mm-hmm.
And so if it's really a holographic theory, one might expect that that this extra dimension is somehow emergent. That's what the idea in ADIA CFT was. And so perhaps that should be a limit of something else, or a discretized version of this.
Yeah.
I just wanted to see if you had any comments regarding the degrees of freedom presented in your talk versus the ones an old-fashioned holographer might expect.
Yeah, so this is why I emphasized at the beginning that the different corners and sides of the Penrose diagram, which are very different from, let's say, ADS. And it's because of the fact that the boundary is null and induced metric degenerates. And then we have these corners where we have to specify what happens to the fields. And so the asymptotic structure is much more complicated. But the things that I can say is that the S matrix does look like a 2D correlator. The asymptotic symmetries of asymptotic flat space, which is not just a statement about exactly the boundary, but you have these fall-offs in 1 over R. So the symmetry generators also have terms that, subleading terms. They are generated by these 2D currents that I've talked about, the stress tensor, supertranslation current, and others for other theories. So there's a clear statement there that relates 2D to 4D. Now I know that most people who come from holography would like to see a third direction there as well. But it isn't too much concrete that I can say about that. The thing is also that we're not just we don't have 2 celestial spheres, one in the past and one in the future. It has been argued that there should be one, and we should just label the states. Another aspect is that if you want to recast all these expressions that we have in the celestial CFT in terms of more normal looking, well, normal because one has a bias from the CFTs that one knows, or ADS CFT, if you want to recast this to look more like expressions in vanilla CFTs, let's say, then we have to reorganize the way we think about scattering. So it has been proposed that we should have a different way of relating, not in and out, but northern and southern states defined. So there has been a lot of work in trying to see if we reorganize our way of understanding scattering such that it looks more normal. And that is rather different from what we do in ADS CFT. So I don't have really a concrete, intelligent remark on what you would like to know. The clear statements that can be made involve this 2D, 4D, and the fact that the Lorentz transformations in 4D act as global conformal transformations on the two-dimensional celestial sphere is underpinning a lot of these statements.
But ultimately, you're repackaging all of the four-dimensional degrees of freedom into this sphere through some Fourier transform type.
Yeah,
thing.
exactly.
Okay, thank you.
Yeah, there's probably much more, but already this repackaging, as I just mentioned, has a lot of exotic features, and yeah, a lot of work is going into understanding these exotic features or recasting them into something that is more amenable. Like having distributions all over the place is not very convenient for understanding basic aspects of CFT, like for example, the conformal block decomposition, where you cannot just nicely factorize things if you have a constraint. Yeah.
Next question is by Enrico.
Well, actually, my question was very closely related, but to some extent, Dion has addressed the question, but I want to press on just to see that if I understand, I wanted to better understand this codimension too. And so in ADS, we think that we can grow an extra dimension by probing the theory different energy scales. Here, as far as I understand, we don't have this intuition, but is at least, does it seem plausible that we will be able to reconstruct the full bulk of Minkowski? And I guess yes, but what does that notion of distance from the null infinity correspond to on the CFT? Maybe it's something I don't fully understand.
Maybe I should first ask back to both of you. So you talked about the radial direction more so than the time direction, which I have.
Oh, no, both of them. The distance from the null boundary. So however you want to measure it, probably it's most convenient to measure it in using U when you get close to V and vice versa.
Yeah, so typically when we go radially, we keep U or V fixed and then just go with R. Yeah, so I think this apparent like difference when comparing ADS CFT to flat space is just because this boundary is null and we have T and R involved in parameterizing the null boundary. I don't know how to make a precise statement that really mimics what we do in ADS CFT at this point. There are many more basic things that we haven't even understood on the celestial side yet.
Let me try to make it maybe more precise, or maybe kind of a simpler question, which is a smaller step just for my understanding. Maybe you said if we have just massive particles, do we expect everything to go, if we are talking about massive particles, everything to go through in the same way that we have a codimension 2 CFT, or does it change?
Yes, but the integral transform is a much more complicated one, right? So I had this, so the Mellon transform is the one for the massless, and then for the massive ones, you have to do this back to boundary propagator.
So that does not seem to be related to the null infinity because they're massive particles. They're not even.
Yeah, they go to time like infinity. Yeah, and they are parameterized by points on the hyperboloid.
So the difference must not hinge on that. On it being a null, future null surface or not, because for massive particle, it seems you still have this claim of a codimension too.
Yeah.
I see. Okay, yeah, thanks.
Next question by Alexander.
Thanks for the nice talk, Andrea. So unfortunately, I also want to push on this question a bit, but I'm going to ask it probably in a much harder this is probably getting ahead of ourselves, but there's going to be some contribution to 2-to-2 scattering coming from the creation of black holes and then evaporation of black holes. And I guess one way to phrase holography that I think we understand in ADS is to say that, you know, the number of degrees of freedom of these internal black hole states, even if you don't know what they are, they scale with the area, not the volume. Mm-hmm. And so is there a way to even like ask that question in celestial holography? Like, how would you count the number of internal states that appear when you try to create a black hole?
Well, we haven't discussed black holes yet in this context. So, I mean, I showed you that if you wanna, there are conformal primary backgrounds, but they are highly boosted. So they are not, for black holes, you would wanna look at spacetimes that are Petrov type D, and these highly boosted ones which transform with definite weights are only Petrov type N. So that's one point. Then second, this question is getting a little bit ahead of ourselves, or actually a lot, because right now we are still discussing perturbative scattering, and there are a lot of things that aren't understood yet.
Yeah, I guess I was just wondering, like some related to what Dio was asking, like, you know, in ADS, you can count the number of states that you have, say, for perturbative fields around ADS, mm-hmm. and that does grow with a volume worth of degrees of freedom. And somehow the miracle of holography is that at sufficiently high energies, it's really black hole microstates, and there's sort of much fewer of those than a volume worth. So I was wondering if, like, in this way that you encode the radial direction, is there a way to see that the number of states caps off somehow? And so
first, maybe I should say that classically, this goes into direction central charge and so on, and classically all the central extensions are 0. And you need to either, for example, the level of this current algebra that I showed you, that came from either you can get central extensions by looking at loop effects, or by non-local effects, like you're looking at the correlators of Wilson lines. But here the story isn't even fully developed. So central charge, for example, is classically 0. And otherwise will probably depend on the RI scale, like the level did. So the level was given by the Caspanomos dimension for the leading soft graviton, the super translation current. So there's even many more basic questions before we even dare to think about black holes that are to be answered first. And it has to do in part with the fact that these correlators look rather different from normal CFT correlators. The conformal dimension is complex. We have all these delta functions. We have the fact that we don't have a split into low energy and high energy. We're probing all boost states. Mm-hmm. So maybe this is closest to your question, that the objects that we are studying are really not following a Wilsonian paradigm here.
Thanks.
These are all super interesting questions. I wish I knew the answer to them.
Gaston, you had a question. You still want to ask it, or?
Yes, no, yes, just again, I will make a paraphrasis of Dio. Just Dio, correct me if I'm wrong. But his point, I think, was the fact that, okay, in standard holography, namely ADS CFT, you have this emergent radial direction. I'm talking about the radial direction. The emergent radial direction as the randomization group flow. Or if you want to become postmodern, you can say information, okay? While here, actually, in contrast, what you have is that this Merin transform which integrate all along the energy, okay? So in that sense, it's the packaging. Somehow it is in a funky way, in a new way, something you have to give up because it's different in the scenario. You also have this idea of flow of energy, encapsulating actually in the Merin transform. So in that sense, it's different, but it's in the same spirit somehow. somehow you are encoding the flow of energy anyway. Of course, mutatis mutandis is different in general, no? But in my opinion, is by definition holography, in the sense that if you can encapsulate these observables in terms of correlation functions of a CFT, I think. And this is also related to the direct question, no? Suppose you want to change the realization of supertranslation by the diff S2. In that case, this would radically change the picture, because if you have diffeomorphism invariant in the boundary, it wouldn't be a CFT strictly speaking anymore, right? It will couple it with gravity. So in that sense, it's not clear to me what you would win, you know, because having gravity in the boundary as well probably become interesting anyway, because it's a lower dimensional theory, but it still will be, this would be a drastic change, right?
Yeah, so in that sense, thanks for the great comment, Gaston. In that sense, the celestial CFT with just the stress tensor that is a local conformal killing vector is the sort of minimal extension that allows for local enhancement of conformal symmetry, but it's also the sort of maybe the maximum where we don't have to worry, where we can still talk about theory without gravity on the boundary. And what Gaston referred to is that the metric that I've written down in one of the first slides, we have to change the boundary conditions that keep the angular piece of the metric fixed, because it will change when we allow for difference 2. So you don't have just the fixed unit 2 sphere, and you don't have it just violated by at a point, but it now can, it changes. Yeah, and so that will make things much more complicated. And yeah, also emphasizing again that we are integrating over all the energies. So many of the statements that maybe these questions are sort of based on will have to be translated into different kinds of questions that maybe talk more about the structure in terms of the complex delta plane rather than energies.
Okay, so last question by Loga.
Hello, hi. Thanks for the nice talk. And I just wanted to ask one broad question about the celestial CFTs. The question I wanted to ask was, what information about the hard particles are really there in the celestial CFT? As an example, let us say, you know, like if I have a massive particle in the bulk, which I integrated out to get an effective field theory, is it understood how that kind of a thing will show up in the celestial CFT? And yeah, and how does it connect to this Wilsonian versus anti-Wilsonian statements and so on? Yes.
Yeah, so
that's what I wanted to know.
When I talked about the soft, the conformally soft sector, I focused on this particular subsector, but the operators that we have that describe scattering of massless or massive particles that are not soft is also captured. And this is, for example, the Mellin transform of plane waves will give operators that, well, operators with a conformal dimension that's not conformally soft, and these correspond then to general finite energy states. So I hope I did not give the impression that this is only about soft physics. I highlighted the soft physics because that's a subsector where we have a handle on getting 2D effective models that describe the symmetry breaking dynamics and so on. But otherwise, for example, also here, the OPE limits, you know, pick your favorite amplitude and take the collinear limit. And then a collinear limit is not exactly the same as taking things soft. Similarly, here when we, maybe here, when we talk about celestial amplitudes and their UV behavior, we're just integrating over the energy. We're not taking any soft limit. So this is not just about soft physics. The soft sector is particularly, seems particularly amenable to a 2D effective description, where we can actually have toy models, because we are still looking for an example of a celestial CFT whose dual bulk we can nail down and have a dictionary between the two.
Yeah, and I was just also asking about integrating out massive particles. Do we understand how that shows up in the celestial CFT?
So there have been so one thing maybe not quite related, but it just came to my mind is the if you have higher derivative corrections in the bulk, they change the soft factors in the soft theorems, at least, for example, the most subleading ones, for example. And you can also keep track of what that looks like in the conformal basis. Specifically to your question, I don't recall now if this has been addressed in the literature yet. Yeah.
Okay. I mean, but
Other than the
you do
statement,
agree that this should be addressed to understand? Is that right? You know, like that is. I'm not wrong in saying that.
Sorry, say again.
That this question is relevant to this question of what happens when you integrate out hard particles is relevant to the question of how Wilsonian or anti-Wilsonian celestial amplitudes are. You know, like, would you agree with that statement? Or?
Okay, so again, the situation is a bit it's made complicated by the fact that we're integrating over the energies to get the new amplitude, the correlator. So a priori, any limits that you take, anything that you do, taking energies to certain limits or integrating out certain energies, one has to be careful what that means after you, what that would correspond to. So a priori, even in the soft theorem, you would not have, a priori would be surprised to say that a zero energy limit survives integrating over all energies and becomes another universal behavior. But of course, because it's a universal behavior of the amplitude, it should not care about the basis of states. And then we saw that taking the zero energy actually corresponds to taking something else to certain limiting values. And that was the conformal dimension, which was introduced by doing this Mellin transform. Now, any question that you have about amplitudes, where you do something with the energy, one has to be careful to what that maps. And I don't know the answer to all possible questions. Here, it's what I just mentioned came from the fact that that you had this behavior or this analytic behavior of the amplitude that Mellin integrals in this low energy limit turn into these poles in the amplitude. But in general, for whatever kind of question that you asked, that does something to energies, integrating out energies, one would have to think what that means for the celestial amplitude.
Okay, thanks.
Maybe look at these references that discuss the ultraviolet behavior, and there's some interesting story going on when either you stay in field theory or you go to a full to the quantum gravity theory. Maybe that gives you a hint of what you would like to know.
Okay, so thanks very much, everyone, for the very nice session. Let me again invite you to continue discussions in GatherTown if you have any more questions or things you want to discuss. Otherwise, we'll meet again at 3 p.m.